Lesson 7-5, Similarity in Right Triangles. We're going to look at the altitude of a right triangle and how that breaks the triangle into similar triangles. What this does is it divides it into two triangles that are similar not only to the original but to each other as well. It helps to look at how this is broken down. In our big triangle, triangle ABC, we have a hypotenuse, we have a short leg, and we have a long leg. When we look at the two that are broken apart, we can match those pieces up. So in this triangle, we have our hypotenuse, this will be our short leg, and this would be the long leg. And in the other one, we have our hypotenuse here, this is the long leg, and this is the short leg. So notice that when we pull these out, the long and the short leg form your altitude. So your long leg will not be the same in both triangles, nor will your short leg. Be very careful the way you name this. If I'm looking at triangle ABC and talking about similarity, I would need to name this triangle ADB, and the green one would be triangle BDC. That maintains proper order with our similarity statement. So the altitude of a right triangle theorem states that if triangle ABC is a right triangle with right angle ABC and BD as the altitude, then triangle ABC is similar to triangle ADB as well as triangle BDC, and ABD is similar to triangle BCD. Now let's look at similarity with the geometric mean. For any two positive numbers A and B, the geometric mean of A and B is the positive number x, so that the proportion you see below is true. So let's work with this just a little bit. We're going to find the geometric mean of the numbers 4 and 18. So we'll treat 4 as A and 18 as B and set up the proportion 4 over x equals x over 18. To solve this proportion, all we need to do is cross multiply, which is going to give us x squared equals 4 times 18, which is 72. To solve for x, we would need to take the square root. So x is going to be the square root of 72. We need to simplify that. If you remember how to simplify, if you can find a perfect square, that makes this easy. 72 is 36 times 2, which makes this 6 square root 2. If you don't remember how to simplify radicals, then we need to review that a little bit. One method that you can use is just start to divide until you can get all the way to 1, and you're going to look for pairs. Let me show you what you would do with 72. If you don't see the square, you can always take the number and just start dividing by 2 as long as you can. Once you can't divide by 2 anymore, you move on to 3. Once you get a 1 at the top, you're finished. This is like a cake. There's the candle, the flames up there. And then you're looking for pairs. Each pair of numbers is going to move 1 on the outside. So the outside would be 2 times 3, and the inside would be the remaining numbers that are not circled. So 2 times 1. So what we get here is 6 square root 2. This is very helpful if you don't naturally see the perfect square in the number. Now I want you to stop the video and I want you to go try to find the geometric mean of 6 and 15 on your own. Your teacher will check this in class and make sure that you have this done. Hopefully you got that. We can use the geometric mean to easily find the lengths of similar sides in right triangles. Let's take a look at how that works. The corollary to the altitudes of a right triangle theorem states that the length of the altitude to the hypotenuse of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse. It's a lot of words, so let's break this down. This is my altitude. And so what this theorem is saying is that the altitude is the geometric mean of these two segments, AD and DC. So what that looks like is this right here. So if we want the altitude, that's this part right here, the BD times BD, then what we're going to do is find the geometric mean of AD times DC and then take that square root. Okay? We can use the same thing to deal with the lengths of the other sides of our triangle. If we identify the short and the long legs of the two smaller triangles, we can set up a proportion to find those lengths as well. Notice that what we have are matching triangles, short to long, matching triangles, short to long. So basically I would take this side over, congruent over this side, and this side over this side. Let's try a couple of these problems together and see if we can make that work. Alright, so in this example we're looking for the altitude. If we think about that proportion, we put the altitude here so we can find the geometric mean. To find that, we use the two segments of the hypotenuse. So we would have 2 and 8. When you work this out, you're going to get x squared is 16, so x would have to be 4. Alright, so here's another picture, and we've got corollary 2 here. We do need you to make a correction in the wording here. We've left out a word. Corollary 2 says that the altitude to the hypotenuse of a right triangle separates the hypotenuse so that the length of, this should say a leg of the triangle, is the geometric mean of the length of the hypotenuse and the length of the segment of the hypotenuse adjacent to the leg. Again, a lot of wording, but what you want to break it down to is finding an appropriate proportion. If you can remember to keep your triangles consistent and your sides consistent, then you're good. For me, I like to label short, long, and hypotenuse. Start with a hypotenuse because only one side can be the hypotenuse. So for my big triangle here, this is my hypotenuse. This is my short side. This is my long side. Let's look at the triangle on the left now. I'm going to label these inside so that I don't get confused. For this triangle right here, my hypotenuse is right here. My short side is going to be here. And my long side right here. And for the triangle to the right, again I have my hypotenuse, my short side, and my long side. Now that's kind of a messy figure, but it kind of helps you figure out what you're looking at with each triangle. It may help you to reorient and draw the triangles. That way you can see which piece is which. Let's try that. Take a look at these triangles. The big triangle I've done in blue, and if you notice the hypotenuse has two segments, 5 and 4, so I've added those together to make that one 9. The short side of my blue triangle is labeled X, so I've carried that over. The long side of my blue triangle does not have a label, so I haven't put any labels on that. For my red triangle, the one on the left, my long side is 5, and my hypotenuse is, not Y. My short side is Y. Let me fix that. And then in my green triangle, I've got a hypotenuse of X, my long side is Y, and my short side is 4, and this is the triangle on the right. We can use this to set up proportions to find X and Y. So when I look at this, I want to find something that only uses one variable. So for example, if I want to find X, I can use the big triangle and the right triangle to do this. The big triangle short side is X. The right triangle short side is 4. Sorry. And that's all within the same triangle. Actually, I'm going to do it the other way. I want to match your notes. You can do them either way, but I'm going to go ahead and stick with the way you've been looking at this in your notes. If I want short side to short side, it's going to look like this. And then if I'm going to do hypotenuse to hypotenuse, it's going to look like this, pulling those off of the relevant triangles. From here, we just need to work this out. Cross multiply, we're going to have x squared equals 36, so we can see that x would have to be 6. Okay, so now let's look at y. For y, I'm going to need a second proportion. If I'm looking at the red and the green triangles, I should be able to find y that way. I've got the short side here, short side in my green triangle, and then I've got the long side and the long side, and then I can just cross multiply. Oh, that should be a y. So when I cross multiply, I'm going to get y squared is 20, and then y would be the square root of 20, which I can go simplify to 2 radical 5. Let's try another one. This should be easier with just one variable. I'm going to go ahead and label my hypotenuse, my short, and my long side for the big triangle, my hypotenuse, my short, and my long sides for the left triangle, and my hypotenuse, my short, and my long side for the right triangle. If you look at where your variables are, you should notice that they are on your short side and your hypotenuse. So let's set up a proportion going short to hypotenuse. I'll do it this way. All right, my short side is x, and my short side in the big triangle is x plus 3. My hypotenuse in the right triangle, the green triangle, let's color code this for you, is x plus 3, and in the blue triangle, my hypotenuse is 12. So when we solve this, I've got x plus 3 times x plus 3 equal to x times 12. Remember that you have to FOIL this out to get this multiplied. So we have x squared plus 3x plus 9 equals 12x. When we have a quadratic or an x squared in your equation, you're going to have to get this equal to 0. So I have x squared plus 6x plus 9 equals 12x. Moving the 12x over, I've got this. And then we're going to go factor. So I'm looking at factors of 9, which would be 1 and 9 or 3 and 3. I need matching signs because of that positive, and I need them both to be negative because of that. So I can see that this is going to give me what I need. And when I go through the work to factor this, I'm going to have x minus 3 times x minus 3 equal to 0. Each one of those, when I set equal to 0, is going to give me an answer of 3. Obviously, I don't need 2 answers of 3, but that tells me that the value of x is 3. The next one is fairly similar, so I'm going to start with my labeling. I have hypotenuse, short, and long. For the left, I have hypotenuse, short, and long. And for the right, I have hypotenuse, short, and long. setting up my proportion with matching pieces.